Hello. Thank you for joining us today for our seminar, Developing Synthetic Aperture Radar Data for Antarctica, Capability Development and Application. I'm Layla Alperslan. I'm the branch head of Geoscience Australia's Digital Earth branch and very excited about this talk today. Before we begin, I'd like to start with an acknowledgement to country. Geoscience Australia values the lands, water and sky as we work to deepen a shared understanding of country and earth. We respect First Nations peoples and their enduring connection, contribution and obligations to country. Reflecting on our shared history, we are committed to listen and learn. Today's session explores how radar satellite technology is unlocking new possibilities for year-round monitoring of Antarctica, seeing through persistent cloud and darkness to reveal important environmental changes. The lack of standardised analysis-ready radar formats limited broader use of this powerful data. Now, Geoscience Australia's Digital Earth is working towards bridging the gap by processing over a decade of radar observations into high-quality, normalised backscatter products that will become freely accessible to users in coming months. Today's presenters will explain why radar satellites are useful over Antarctica and how the data has been produced. Digital Earth has been working in collaboration with the University of Tasmania to demonstrate how the Digital Earth product is providing value by observing and understanding a critical Antarctic habitat. This and future applications will enhance both research and policy responses in a rapidly changing world. We have a few presenters today. First is Dr. Kimberlee Baldry. She is an Earth observation scientist with Digital Earth, where she focuses on improving data quality and usability for monitoring the Earth and ocean. With a multidisciplinary background and a newly awarded PhD in Southern Ocean Biooptics from the University of Tasmania, Kimberlee brings both scientific depth and adaptability to her work. Alex Bradley is an Earth observation data scientist with Digital Earth. His work applies remote sensing to environmental challenges, and Alex's strong foundation in engineering and software development supports his efforts to create high-quality geospatial products and analysis-ready data. He holds degrees in petroleum and chemical engineering and is currently pursuing a master's in space engineering. And Dr. Alex Fraser is a remote sensing scientist and Antarctic researcher at the University of Tasmania, affiliated with the Institute of Marine and Antarctic Studies and the Australian Antarctic Program Partnership. His research spans polar stratospheric clouds to Antarctic sea ice variability. Recently awarded an Australian Research Council Future Fellowship, Alex is leading efforts to understand the extent, thickness and climate impact of Antarctic landfast ice. Please join me in welcoming them, and I hand over to the team. Thank you.
Hello everyone, my name is Kimberlee and today I'm going to talk to you about how our Digital Earth Antarctica program is empowering Antarctic science. To start with, how we're doing this is by developing synthetic aperture radar data for Antarctica. And you can see a beautiful example of some of the data we have processed on this slide. I want to just take a moment to thank everyone who's been involved in this program so far, particularly those listed on the screen, which include our Digital Earth Antarctica team, members from Digital Earth Australia, and also our collaborators at CSIRO. The Digital Earth program delivers free and open satellite data for everyone. The new Digital Earth Antarctica program is modelled off Digital Earth Australia, which historically has delivered Sentinel-2 and Landsat data acquired by the European Space Agency and the US Geological Survey. Now we will be delivering the European Space Agency's Sentinel-1 radar data. These data are being reprocessed for Antarctic conditions using Digital Earth technology to improve data quality and usability. These data will support Digital Earth Antarctica end users to deliver applied science products. The Digital Earth program is being funded by the Landsat Next partnership under Geoscience Australia's new Earth observation program. This means that we'll be able to support long-term studies towards climate change monitoring, Antarctic management, logistical operations and more into the future. But first, let's take a moment to consider why you should care about Antarctica. Antarctica is an absolutely beautiful environment, and more importantly, it has penguins. We all love penguins and the cute penguin video content that they provide. But without Antarctica, we of course do not have penguins. On a more serious note, did you know that the weather that we experience today is linked to Antarctica? The weakening of the Antarctic polar vortex has been shown to have led to the weather patterns surrounding the extreme 2020 Black Summer bushfires. Of more immediate concern, signs of this same weather pattern are emerging today as we head into summer this year. This means that we may experience higher fire risk this season and potentially catastrophic fires. Antarctica is constantly changing, and the only way we can capture this change is across the entire continent is from space using satellites. Antarctica is highly dynamic with lots of ice movement shown by the animation on the right. You can see ice flows happen across all of the continent and are most fast at the edges of the coast. This is where we have ice tongues and glaciers protruding into the ocean, and you can see an example on the bottom right, where we see a month of an ice tongue coming out of the Mertz Glacier breaking off, and these big large chunks of ice will go on to produce icebergs, which are hazards for ship operations in a large portion of the Southern Ocean. And yes, you can even monitor penguins from space. Up in the top right, you can see Sentinel-2 images with these kind of pinky brown smudges. What you're seeing is penguin poop, and this tells us where the penguin colonies are during summer. To understand how to best support the needs of Australian government and Antarctic science, 2 years ago we conducted a scoping study with extensive stakeholder engagement. What we found was that the top priority for end users was to deliver optical surface reflectance and synthetic aperture radar backscatter data. Significant data qualities are required for the Landsat and Sentinel-2 datasets to make surface reflectance suitable for continental-wide applications in Antarctica. There is a lot of inconsistencies in the datasets due to the unique Antarctic conditions, which are considered edge cases of concern on the global scale. We'll be working with our friends at the European Space Agency and the USGS to try and deliver improvements in Antarctica for all users. We also found that there is absolutely no existing analysis-ready data that covers the entire continent for backscatter or SAR for Sentinel-1 radar datasets. Data providers leave Antarctica out of global processing efforts currently because it is more challenging to produce quality data in this region, particularly due to the dynamic and ever-changing landmass. Due to the lack of existing data, the need here is very clear, and so SAR is where Digital Earth Antarctica team have first committed their efforts. You'll notice that there are two modes for Sentinel-1 shown at the bottom right of the screen. We have the extra wide mode, or EW mode, and interferometric wide mode, or IW mode. The IW mode is collected over all of the globe, but the EW mode is specifically only used over large areas covered by sea ice at the poles. As IW mode is also available over Australia, we have been first collaborating with the Australia team to build Geoscience Australia's SAR backscatter capability over 2 entire continents. So the differences of SAR compared to optical really adds value to the existing service provided by optical sensors. SAR observes shape and roughness compared to optical, which observes colour. SAR is an active sensor which interacts with the ground, also giving us the ability to observe moisture content. Unfortunately, SAR's geometry is a bit more complex, and existing expertise within Geoscience Australia is limited. Our team has undergone extensive training in order to build Geoscience Australia's capability in this area to deliver a high quality and valuable product to our end users. So watch here as the animation rolls into winter months. You can't see anything when you use optical imagery. And when you can see it, it's often obscured by very high cloud coverage. SAR offers us the capability to observe through darkness and cloud, which, as you can see, is very important in Antarctica. SAR also provides new information on Antarctica's snow surface. You can really see the differences here between the optical and the SAR images. The optical image looks, well, mostly white due to the snow. You can see some shadow and texture. However, when looking at the SAR image, you can see even more. You can really see the big crevasses that are hidden underneath the snow. Over here. You can start to get a sense of how deep they are and how big they are and their extent. You can also see more of the texture and the flow tracks of the glacier as it flows and moves out into the continent, the ocean. Having a look at this image, it might look a bit strange. It took our team a few weeks to understand what was going on with this black region down the bottom, and a few lectures from our friends at the Alaskan Satellite Facility. Over Antarctica, SAR penetrates snow, and so much so that all of the signal is essentially lost, giving these big black patches across the continent. If you look at optical imagery, it indeed should be white, but SAR offers this new depth of information that is unable to be captured using optical satellites. We can also look at differences between summer and winter. Summer, you experience melt, and so the snow often appears darker compared to winter, where the frozen snow appears whiter. And I'll explain this a bit more in this slide. So using microwave scattering theory, you can really start to unlock a lot of information about Antarctica, which isn't really there in optical. Like I said, in the dry snow zone, most of the signal penetrates into the snow and is attenuated at depths. So you get very little coming back towards the satellite sensor. The percolation zone is where snow is refrozen and it's more dense. This appears very white, as you saw in the previous image. This is because a lot more of the signal is reflected back on these surfaces. As snow becomes more wet and has more melted moisture content in it, you get a lot more signal reflecting away from the sensor, as this is how the microwaves interact with the water molecules. So the snow appears darker as it gets more wet again. Moving on to more glacier ice and sea ice surfaces, you get more of a scattering happening from the roughness, and the degree of scattering coming back to the sensor is controlled by how rough the surface is. Smooth surfaces are darker because more signal is bounced away from the sensor, whereas very rough surfaces are brighter because more signal gets bounced back towards the sensor. Over open water, SAR imagery appears black because almost all of the signal is reflected away from the sensor. So that's just a bit of SAR 101 to give you a bit of taste of the depth of information that comes from this imagery. A final highlight of SAR is interferometric SAR, or INSAR. This uses wave phase information to detect and monitor ground displacement changes. This has some important applications over Australia and Antarctica, including understanding groundwater in Antarctica in Australian reservoirs, glacier flow in Antarctica, and detecting stationary sea ice along the frozen continent. On the right, I show an example of how we can use INSAR to detect what's called grounding lines in ice sheets. At the edge of a continent, we often have ice shelves which float on the water, and these ice shelves move up and down depending on the rise and the lowering of ocean tides and sea surface height. SAR tells us where the motion stops, and this is when the ice sheet is firmly stuck to the ground and doesn't experience any of this change in elevation due to the ocean. With SAR backscatter products and surface reflectance, Digital Earth Antarctica can unlock continental scale application to produce a wide range of products. We are still a few years away from producing all of the products you see on this page, but we are beginning to work with scientists under Australian Research Council grants and Australian government-funded programs to develop these. Our last speaker has been working with us over a few months, collaborating to produce a fast ice product for the entire Antarctic coastline. It is important to remember that no existing readily accessible continental scale SAR analysis-ready data is currently available, and Digital Earth Antarctica is trying to change this to unlock large-scale science products to deliver analysis and insights across the continent. Our SAR backscatter product is coming along well. Users can easily access and visualize the data using a standard access endpoints in Python, Open Data Cube, and GIS environments. This quick visual analysis shown was not possible before without extensive data processing and manipulation. We are really unlocking this data for more users with lower technical capabilities, like policymakers, saving time and money through easy access and analysis. In our program, we have actively tried to engage with our large end users and stakeholders, whose logos you can see at the bottom of the left. We have engaged with them not only at the start of the project during scoping, but as soon as we've had products being produced from prototype pipelines. This involved providing small data sets to end users to explore and provide feedback through regular meetings, emails, and even a hackathon. This has helped us to identify improvements to our data product along the way and upskill end users and GA staff in the process. The hackathon was particularly efficient in delivering outcomes, providing our technical teams with instant feedback and stress testing, promoting new innovation and collaborations, and increasing our end user uptake. We are also further developing digital Earth tooling and web mapping services to deliver continental scale views and time series analysis over Antarctica with just a few mouse clicks. Users will be able to interact with Antarctic data through the Digital Earth Maps portal and within their GIS programs of choice using web mapping services. This will allow users like policymakers and analysts who often have minimal technical skills to use our data in their day-to-day workflows. By doing all of this, Digital Earth Antarctica will deliver impact through the Australian and Antarctic program, which will then flow on into international treaties and initiatives like CAMLR. Antarctica is a complex environment to manage and protect, with multiple layers of legislation across a very large continent. Long-term continental scale products will better inform us on how the continent is changing, allowing us to better protect its vulnerable and fragile ecosystems. Thank you so much for coming to learn about our program and about SAR data. If you want to test our SAR optical products for your use over Australia and Antarctica, please participate via the QR code and we'll get back to you when our data is available. Thank you. I'll now pass on to Alex Bradley, who will tell you about the technical difficulties and challenges that we've experienced in producing this data in our program.
Yeah, awesome. Thank you, Kim. I think that's such a great introduction to what I'll be talking about. Yeah, so as Kim mentioned, this has kind of been a 2-year journey for us. So today I'll take you through some of the challenges that we've faced, particularly dealing with Antarctica and its complexities, as well as kind of introduce our product a little bit further and talk you through some of the technical detail that has gone into producing this data set. So yeah, again, thanks to all the contributors that have been with us along this journey. So just beginning with some of the key challenges that we've faced when doing this. So firstly is the fact that we're dealing with very large data volumes. So I'm sure many people here who have worked with satellite data over kind of extended periods of time understand that issue. But from our perspective, it's kind of in two facets. Firstly, in us getting access to data that we want to process, and secondly, in how we want to store the products that we made. So we really need to be smart about how we kind of work with these large data volumes. Secondly, as Kim alluded to, with SAR, there's the complex geometry that plays into the way that these sensors look at the Earth. And so terrain and the different shapes that we see in Antarctica have large effects on the data that we get back. Third is that we have a whole host of different SAR processes and options that we can use to actually make this data. So for us, it was really important to understand what the differences were between these processes and what kind of settings we should use in order to make the best product that we could for the users. Dealing with polar projections. So typically elsewhere around the world, we can sort of deal with latitudes and longitudes, but that really falls over when we start heading down south. So we have to uplift a lot of our technology to be able to handle kind of working with and visualizing Antarctic data. And finally, this is an especially difficult one, is that we're actually dealing with kind of a moving target. So Antarctica is very dynamic, as we saw through some of the slides that Kim has shown earlier, and kind of being able to account for this with SAR data that we produce is quite difficult. So we did a lot of work kind of understanding the impacts of that. So firstly, just beginning with the data volume side of things. So Sentinel-1 goes all the way back to the end of 2014. So we're looking at over 10 years of consistent coverage across the continent and across the globe as well. So we have these three pictures here. On the left, we have Australia's coverage in the interferometric wide mode. In the middle, we have Antarctica's coverage in the interferometric wide mode. And on the very far right, we have this extra wide mode, which is kind of specific to Antarctica, where we sort of reach out into the broader kind of sea ice and polar region zones. And one thing you'll notice is that there's a bit of a hole with Australia here, and that has to do with the fact that there was a failure with one of the satellites. So the coverage does change a little bit when we have one or two satellites operating at any given time. Another thing you can kind of notice quite quickly is the fact that we have a lot of coverage in the Antarctic region, and that's basically due to the orbits of the satellites which pass over Antarctica essentially at any given time. So we're getting a lot of repeat observations of the area. And in terms of data, so as I said, we're dealing with huge amounts. In Australia, we're looking at around a petabyte, and with the RW mode, which is where we're starting for Antarctica, around half a petabyte. And once we kind of extend into the EW mode, we're dealing with an extra petabyte. So yeah, a very considerable amount of information to deal with. So we have to be smart with how we do that. So when we talk about our product, I think this slide really says it all. So this is the first analysis-ready data product that we're producing, which is called normalised radar backscatter, or NRB. Sometimes it's also referred to as gamma naught backscatter. But essentially, because the instruments of the SAR satellite are side-looking, what you get is these really kind of predominant impacts of terrain. So when a sensor looks at a mountain, the face of the mountain, which is looking towards the sensor, appears really bright, and the backside of that appears really dark. And this is kind of not ideal when you're looking at time series analysis, because if you're looking at the same area from a different geometry, the way that scene looks will be very different. So what you want to do is called normalizing that data. And what that does is essentially provide a consistent surface where you can really understand what's happening on the ground, as opposed to what's being introduced by the geometry. So this is essentially the process that we're undertaking. And there's a lot of guidelines which kind of dictate this, and also, as Kim mentioned, looking at things like SAR as well. But this is the first kind of product that we're looking at. So to get to that point is a bit of an involved process, and there's really three main steps. The first is something called geocoding. So when we get a SAR image, it's in what's called radar coordinates. So it doesn't really have any idea of where it is on the ground, and we need to place that information on the ground. And to do that, we need to understand the positioning of the satellite and also have some understanding of the surface of the Earth. Once we get that SAR imagery onto the ground, we need to do something called geometric terrain correction. And again, this has to do with the way that the SAR instrument looks at the satellite. So you can kind of see here these ridges that the bright side, or the side facing the center, is really compressed and the back side is quite spread. So through geometric terrain correction, we can kind of normalize across the terrain and get the pixels where we want them to be. And the last and most importantly is that last step I mentioned, which is about correcting the brightness essentially for the terrain impacts to get our normalized radar backscatter. And you can see that a key sort of input along this whole process is a digital elevation model, or essentially a digital representation of how high the Earth is at any given point. So as I mentioned earlier, one of the big challenges for us was essentially, there's too many options, there's a lot of workflows. So we really wanted to understand, which was going to be the best or most fit for purpose and what the impact of our decisions were. So the three main processes that get used are Gamma, SNAP, which is from the ESA, and ICE3, which is a new release of the software from JPL. So Gamma has historically been used within Geoscience Australia, and it's a proprietary or licensed software. SNAP is free and is used quite broadly across the industry and in Antarctica as well. And then finally, we have the newly released ICE3, which is open source, so it's quite easy to sort of contribute to these sorts of projects, and it's being used for the NISAR mission, which is another upcoming radar mission. So and I won't touch on it too much, but there's also some kind of fundamental differences in the way that the software actually do their job. But the newly released ICE3 has this, what we call adaptive multi-looking, which is kind of the next step in the way that these processes have worked in the past. So essentially what we wanted to do was assess the products that we got from these three processes. So I won't go into too much detail into everything on this slide, but the way we did that was through building what we called a quality framework. And really what we're doing here is we're understanding the quality of the products that come out of these processes across a whole host of different things. So understanding geolocation, how well it gets put onto the ground, radiometric quality, how well we correct for terrain, and all those sorts of differences. And we were able to do this across both Australia and Antarctica because this is a joint joint project with Australia as well. And we're kind of doing it across a whole host of different areas with different topographies, terrains, and those sorts of things. So just to talk through a couple key results when we compared these software. First is geolocation, which, as I said, is essentially the ability for the software to put the image correctly on the ground in the correct location. And the way we do that is through using something called corner reflectors. So these are these triangular looking things. And when the SAR sensor looks at those from space, you get a really, really bright response. And essentially you can compare that response you see in the image to the known location of these on the ground. And through that, you can build an understanding of how accurately we're putting this information on the ground. So if we do that for all of our software, we get something like this, which essentially shows the error. So closer to the center means we're really good at putting things on the ground, and further away means that we're getting some variability and potentially some shakiness in our geolocation. So we have ICE3 in red, we have the Gamma-based softwares in orange, and we have two different SNAP-based workflows in green and blue. And the dotted lines are what happen when we also apply some form of atmospheric corrections. And so the first thing you notice is that these SNAP-based softwares are actually quite far up here. And this was due to a bug which we were able to identify and kind of feed back into ESA. And so now these results are actually looking a lot better. But firstly, I think the big thing to know is that we saw that the best geolocation results were with ICE3. So we saw a really kind of stable location over time. Secondly, as I said, we're kind of getting similar sorts of accuracy with SNAP and Gamma once that bug had been resolved. Thirdly, the atmospheric corrections have a pretty big impact on how we're able to put this data on the ground. And finally, this was over the Surat Basin corner reflector network in Queensland, but we also have some Antarctic corner reflectors as well, and we're able to kind of compare the results, and we saw very similar things there, which is obviously very positive. So stepping over to another aspect of image quality. So here we have a really beautiful SAR image of Heard Island. And if people who have been paying attention to the news, we actually set foot on Heard Island for the first time in about 20 years, I think it was, recently. And so what we can see here is just a comparison of the image quality that we get out from each of these processes. And they do look quite similar. There are some differences. So, for example, some darker speckle that we see through Gamma. But really, the takeaway from this is they actually are quite similar in the results that you get out the other side. But when we do some more detailed analysis, we kind of start to see that ICE3, particularly in very rugged terrain, does a little bit better. So moving on to some of the challenges. This one, for anyone who's worked with Antarctica, is a very fun one. Typically, you'll see a map of the Earth in latitude and longitude, and we get Antarctica, which is looking like a nice squished pancake down the bottom here. But the Earth is actually a sphere, as I hope we all know. So these 2 points at the end here are actually joined. And so when we're dealing with data that's often in terms of latitudes and longitudes, we have a lot of difficulty dealing with this with data which moves across these points, which is called the anti-meridian. So the solution to that is a different projection system. And so down here, where you typically see Antarctica in a nice view, is a polar stereographic projection. And we can see that now the anti-meridian is represented a lot better, and we can kind of better express data across this point. But this isn't simple because so many systems work with latitudes and longitudes. We've had to do a lot of work to kind of uplift our technologies to be able to handle that. And from the software perspective, in terms of functionality, again, really important to understand. We were seeing some failed scenes through SNAP, but through ICE3 and Gamma, it was fairly straightforward, which was good to see. Another challenge, this one, is very interesting. As I said before, Antarctica is a very dynamic environment. And so when you're inputting a digital elevation model to try and correct data, you have the potential for kind of introducing artifacts as well. So here, for example, we have our uncorrected radar image. We're going to feed it a DEM, which is kind of static across time. And the output of that is the corrected image. And what we can see is that we have these real crevasses kind of carrying through from the source imagery. But by actually applying these corrections, we're now introducing some artificial crevasses into the data. So depending on your application, this might not be an issue, but for someone who's interested in crevasses, then obviously there's an issue there. So this is led to a really exciting piece of work that we've been doing with the Polar Geospatial Center at the University of Minnesota, and that's looking into something which are called multi-temporal DEMs. So essentially, rather than have a static DEM, which is fixed in time, we're looking at having a DEM produced on an annual or even more frequent basis to try and account for some of these changes that we see. So this is something which typically isn't done, but for Antarctica, we're looking at seeing if it's potentially going to help us. Another benefit, to ICE3 is something called static layers. So just to maybe begin with the animation, as I said before, when we're introducing these artifacts, depending on what the use case might be by the user, we want to be able to offer different forms of data. So using our static layers, which we produce alongside the data, we're able to essentially reverse the correction and get it to another format of data. So this is the original radar image, but there's also other formats which I won't go into, for example, Sigma Naught, which is widely used across Antarctica. So really, we just kind of want to enable this flexibility. And so another benefit to using static layers in the way that we are is essentially you're able to share data layers across different products. And what this leads to is a really big saving in cloud storage costs, which operationally is obviously a big plus So this was another thing which was really beneficial to ICE3 compared to the other softwares. So I think just to tie it back into the start and how we address some of these challenges. So large data volumes from the acquisition side and where we're getting our data from. We've had a really strong partnership with the Copernicus Australasia Data Hub, and they've been doing a lot of great work to get the petabytes of information that we need for our processes across. So it's been really good to work with them. From the other end of the side, so storing our products, where we're making use of smart things like static layers. The complex geometry, again, we have the benefit of kind of being able to rely on these established and kind of well-maintained softwares for ICE, such as ICE3, for example. Again, different SAR processes. Thanks to our evaluation framework, we were able to kind of understand the differences that we've made, that each software introduces, and support the use of ICE3, which is kind of our final decision moving forward. Polar projections, this is an ongoing thing where we're looking to uplift our technologies, but there shouldn't be too many issues with doing that. And finally, fast moving terrain. As you saw before, we're kind of investigating a whole host of different methods to kind of address these and minimize the artifacts as best we can. So just to kind of tie it back, and I guess maybe a final slide. So this essentially is our product. Maybe while I go through these dot points, you can watch this cool animation of the Erebus ice tongue, which is an ice tongue kind of slowly moving out towards the sea and breaking off over 10 or so years. So the first, and I think really important point, is that these are analysis-ready data sets. So essentially all of the things I've just talked through, we've kind of removed from the user having to do, and they can now come and use our data. We're going ahead with the ICE3 software at a 20-meter resolution, and we're going to have a fully processed archive, so all the way back from 2014 to ongoing, and we expect that to be released in early 2026. We're using Antarctic-specific DEMS to try and reduce those artifacts, and also implementing static layers to kind of keep storage low. And another thing I haven't touched on too much, but it's also been a really great opportunity for Geoscience Australia to strengthen our ties with some of the other space agencies. So there's been a lot of back and forth with them, kind of getting feedback, and also us being able to contribute to their software as well. So where we are, where we are today, we have some sample data which we're producing for users. So this is an example through the Explorer where people can go understand coverage and get the data they want. But as I mentioned, we expect the full kind of data set to be available early next year. Just touching on future work. So this has all been relative to the IW mode. But as we've talked about, the EW mode is very important to Antarctica as well. So that'll be our next port of call. And then beyond that, looking into INSAR capabilities. Excuse me. So at the bottom here, again, we can see the Erebus ice tongue, and you can kind of understand how combining backscatter with INSAR could lead to some really cool insights. So this is essentially where we're looking to the future. And yeah, I think I'll leave it on that, and we can pass it over to Alex, who's going to talk us through some of his awesome results with fast ice. Thanks.
Thanks, Alex B. I'll just share my screen. So I really want to acknowledge the huge contribution to this project from especially Caitlin, Kim, and Alex at Geoscience Australia. Without these guys, this project wouldn't really get off the ground. But let me introduce myself a little bit more first. So my name's Alex Fraser. I'm a research scientist at the Australian Antarctic Program Partnership, which is hosted at the Institute for Marine and Antarctic Studies at the University of Tasmania. And yeah, today I really just want to let you all know about an application of the great work that the GA guys have been doing, particularly focused on the EW mode that Alex just talked about. So I want to talk to you today about landfast sea ice, and sometimes we shorten it to fast ice. It's a really bad name because fast ice is sea ice that doesn't move. It's short for landfast. But basically, we like to call it the most important ice you've never heard of. It's important for a whole bunch of reasons, and I'll touch upon a few of these now just before we before I talk about the application. So fast ice is locked onto the coast or grounded icebergs around the continent. And you can see it here in this great schematic by this fantastic blog I uncovered the other day. But here in this photo that I took a couple of years ago, what you can see here is these little dots. These are grounded icebergs. So these are icebergs that have calved from ice shelves, but they're deep enough to touch the bottom of the seafloor on the continental shelf around Antarctica. And by seeding these little points of stability all around the continental shelf, what we get is landfast ice extending sometimes 50, 100, or even 200 kilometers from the coastline itself as a thin cover of sea ice, 1 or 2 meters thick, which doesn't move with the currents and the winds, unlike the pack ice that I'm sure you've all seen. Fast ice is really important in the breeding cycle of emperor penguins. You might have all seen this March of the Penguins, this documentary about the emperor penguins around Antarctica. All of that was shot on fast ice. And you can see here in this photo that I got from the Australian Antarctic division, emperor penguins use the fast ice to breed and to raise their chicks on. So here's a schematic of the breeding cycle. So fast ice forms every year in around March, April, May, reaches its maximum extent in September or October, and breaks up from November onwards, basically. And this coincides with the arrival of the adult emperor penguins at the colony, laying the eggs hatch, and then the chicks get born and get looked after by the adults. And here's an example colony. So there's a big emperor penguin colony at Dumont-Deville Station, which is basically south of Australia. The adult emperor penguins need to walk from the colony to the nearest open water in order to feed and then bring that food back to the babies at the colony. So they have to walk dozens of kilometers frequently in the middle of winter. And so as you can imagine, the amount of fast ice that separates the colony from the feeding grounds has some bearing on the success of the breeding. And you can see here this figure from a paper by Rob Massam in 2009 shows the distance from the colony to the open water and the breeding success on the y-axis. And you can see that when the distance to the open water gets too large, the breeding success drops. But the penguins still need some stable ice. So there's this trade-off between having too much ice, meaning that they have to walk too far, too many times, versus having stable enough ice for those chicks to successfully get reared in the creche stage. And we've seen big changes in Antarctic sea ice in the last decade, really culminated in 2023, where we failed to grow about 3 million square kilometers of sea ice around Antarctica. It's a huge crash in the extent, and it's got a lot of people worried. It had a bearing on the breeding success of emperor penguins in this area of West Antarctica in 2022. So there wasn't enough stable landfast ice to have a successful emperor penguin breeding in that year. There's a whole bunch of other roles that fast ice plays, not just in the ecosystem, but also in the oceanography with global implications, actually. So fast ice, which is indicated by a white in the schematic here, is quite often associated with these things called coastal polynyas. So these are intensive regions of sea ice formation that come about because the very strong and persistent katabatic winds flowing off the continent create an area of open water in certain persistent locations. In these locations, there's no sea ice cover to act as an insulator between the relatively warm ocean and cold atmosphere. So we get very intensive sea ice production happening in these locations. And because brine gets rejected when sea ice forms, that water becomes very salty and very dense. And if that water can then flow off the continental shelf, it goes on to form what's called Antarctic bottom water. And Antarctic bottom water basically drives the lower limb of the global thermohaline circulation. So it's a very important current, and it's directly related to the amount of fast ice around Antarctica. As I mentioned, sea ice has dramatically crashed over the last decade. So we went from unheard of highs throughout the 2010s to unheard of extreme lows from about 2016 onwards, and it's persisted even into this year as well. We can easily map the amount of sea ice around Antarctica, but it's much harder for us to map fast ice. We've done it traditionally using visible imagery, but we have the problem of clouds with visible imagery. Clouds and sea ice are both white, and pack and fast ice look very similar. So there was a lot of manual mapping required to separate fast ice from pack ice. We did this recently. It was a huge mapping exercise, and we were able to map Antarctic fast ice, but it took about 5 years to map 18 years of fast ice. So this is not sustainable in the long term, and we need a much better way of automating than the semi-automation that we were able to do using visible and thermal infrared imagery. Also, fast ice has crashed dramatically as well, not just sea ice, but fast ice is now half as much in the summertime as it was even 10 years ago. So this is a really urgent problem. So in 2024, I was awarded an Australian Research Council Future Fellowship to better understand fast ice. And the main cornerstone of that project was to automate fast ice mapping. The best way to map fast ice is by SAR. We've known this from the Arctic, but we haven't had the analysis-ready data that we needed to really roll this out around Antarctica. And I just want to show you a quick example of how easy it is with SAR to determine what parts of the sea ice are fast. We can see by flicking back and forth between these two 12-day images, a lot of the sea ice doesn't move, and that's the fast ice. And so the challenge now is to use these repeat 12-day scenes as image pairs to automatically map what's fast ice and what's pack. And so the idea is we can process the analysis-ready data in such a way that it enhances the bits that are fast and separates them clearly from the pack ice. And so we've been using Meta's segment anything model to segment the image into bits that are fast ice and pack ice. And then we're using supervised classification to tell us what's pack and what's fast ice. It's working really well. We've got an example from the Thwaites Glacier region here. This is basically the first fully automated year-long time series of fast ice area in this region here. And it's really fantastic to see this come to fruition so quickly and easily with the Geoscience Australia partnership. So the next step now is to roll this pilot study out to the entire Antarctic coast back to 2014, as Alex B just showed us. It would basically be impossible for us to do this without the support of Geoscience Australia. And I've put some numbers here for the storage just for this coastal strip around Antarctica and the processing that would need to happen. But basically it would be an insurmountable problem for an individual research project to be able to do this on such a large scale. And with that, I thank you and open it back up to the panel. Thank you.
Thank you all for that fantastic presentation. We will now take questions from the Q&A section on Teams. There are a few comments that I will just read out so everyone is aware. The recording will be put up on our YouTube channel within 2 weeks. If you would like the slides, it's best to reach out to the presenters after the talk via talks@ga.gov.au. Alex has posted in the Q&A section, Alex Post from the Antarctic team. I'll link to the form if you are interested in trying out our data. There was a question on NRB. Is NRB just gamma 0, or are there other normalisation corrections as well, which Kimberlee has already answered. Kim, did you have anything to add to that question or answer?
No, just to say that NRB or gamma naught is currently the analysis ready data product endorsed by CEOS, the Committee for Earth Observation Science, which is an international organisation. And there are other conventions and normalised products that exist as well, and another one of those is called Sigma Naught, which is sometimes referred to as ocean radar backscatter, and that's sometimes preferred over the ocean. So it's quite complex, and I put some resources in the comments there if people are interested to learn about. But yeah, essentially the answer is yes, there are different conventions, but NRB is currently the only analysis ready data product that is kind of endorsed as an international at an international level.
Brilliant, thanks, Kim. And a question from Salman Khan. I could see some faint differences over the ocean between gamma and gamma 0. On your slide, on land, you have a DEM. Is anything specific done over ocean in the ARD product? You have answered that, and you might have covered it in your last one. Is there anything else to add, or did anyone else have any questions of clarification for that? Fantastic. Without any other questions, I would absolutely love to once again have you all join me in thanking the team for that absolutely wonderful presentation. Our next talk will be by our colleagues, National Resources Canada, and they will be speaking about mapping Canada's future, Geoscience at Natural Resources Canada, and the Geological Survey of Canada. So please join us at the special time of noon on Wednesday, the 5th of November. Details and registration links for all our public talks are available at ga.gov.au/news, and click the public talks tile. So that sounds like a great next talk in November. But again, thank you all to our presentations for today and the questions from the audience. It's been fantastic. Thank you so much. Have a wonderful Wednesday.